this section we're going to discuss, probably in this video, we're going to discuss sections 10.9 and 10.10. So 10.10 looks at hypothesis testing concerning variances. Undergraduates can skip this section. Graduate students need to read this section on your own. Alright, we're going to look at section 10.10 and we're just going to look at the first part of it in this video, and then I'll make another video where we look at the second part. Alright, so we've got a definition here. It says, suppose that W is the test statistic and RR is the rejection region for a test of a hypothesis involving the parameter theta. So the power of the test is defined as follows. So this can be the probability that we reject the null given the parameter is theta. And so notice that when we look at the power here, notice this is a function of theta. So here, whenever we reject the null, that occurs when W is in the rejection region and the way of the parameter is equal to theta. So suppose we want to test under the null that theta is equal to theta naught. Well, then under the null we have that the power at theta naught, because remember the power is a function, so we're looking at this evaluated at theta naught now, is equal to the probability we reject the null given theta is equal to theta naught. So looking at what this is equal to, notice this is equal to alpha. That's our significance level. Whereas for the alternative, under the alternative, theta is equal to theta A. Well, under the alternative, when we look at the power function evaluated at theta A, this is the probability rather, that we reject the null given that theta is equal to theta A, and notice that this is equal to 1 minus beta, or we can think of this as 1 minus beta, where beta is really a function of theta A, because beta is going to change depending on what value of theta in the alternative that we use. And we've seen that in previous sections. So ideally what we want here is we want the power to be large for every value of theta except for when theta is equal to the null. So we want the power evaluated at different thetas to be large for every value of theta except for theta equal to theta null, or theta naught rather. And the reason for this is when theta is equal to theta naught, we don't want to reject the null because it's right on the null. But for every other value of theta, we would like it to reject the null. So typically what these power curves look like is if we have theta naught here, and notice that power is restricted between 0 and 1. So typically what happens is power at theta naught will be alpha, and then as we move away from theta naught in either direction, the power will increase to 1. And we've seen that. The further we get into the alternative hypothesis, the higher the power is going to be. Now, ideally, what we would like to have is we would like alpha, or the power at theta naught, to be equal to 0. In other words, when we're at theta 0, we don't want to reject it all. And when we're anywhere other than theta naught, we'd like the power to be equal to 1. So in other words, beta is equal to 0 for all theta not equal to theta naught. So what this would look like in our graph is when we're at theta naught, our power would be 0, and I want to fill that in, power would be 0, and then up here, everywhere else, it would be equal to 1. But this can't be done. So since we can't achieve the ideal situation, what we do is we start with a specified small value of alpha and a specified value of n, and we find the test statistic in rejection region, which gives us the smallest value of beta. In other words, that's going to be the largest possible power. So let's look at an example of that. All right, so we've got some more definitions before we get to that example. So a simple hypothesis is one that completely specifies the probability distribution of interest. Any other hypothesis is what we call the composite hypothesis. So for example, if we have a binomial probability distribution with n equal to 10, an unknown parameter p, then to determine if we have a simple or composite hypothesis, we could look at these three different scenarios. So looking at our first one here, we've got that under the null, p is equal to 0.2. So in order to be a simple hypothesis, we need one which completely specifies the probability distribution of interest. So notice here, since we have that p is equal to 0.2, we have completely specified that probability distribution. So for this one, it's going to be simple. The second one is going to be simple for the same reason. Now, if we look at the last one, under that hypothesis, we've got p greater than 0.2. So p could be 0.3, it could be 0.4, 0.5. So we have not completely specified which probability distribution of interest we have here, because it could be any of those would satisfy. So for this one, we're going to have a composite. Let's look at another example. Suppose that y1 through yn are IID with mu as the mean and sigma squared equal to 1. So then if we set mu equal to 5, is that simple or composite? In other words, do I now have all the information I need to know exactly what normal distribution I'm working with? And the answer is yes, I do. This one is going to be simple. Looking at the second one, again, we've got y1 through yn are IID normal. But notice the difference here, we haven't specified the value of sigma squared. We're still going to assume under the null that mu is equal to 5. Notice that this one is going to be composite because I don't know the value of sigma squared that we're working with, so I cannot completely specify that probability distribution. There's an infinite number of normals that could be because there's an infinite number of potential values for sigma squared. So our goal here is we want to find the most powerful test of H naught, or under the null hypothesis, theta equal to theta naught versus the alternative, when alpha is equal to the power of theta naught and sample size n are specified. So notationally, we're going to need to use the likelihood function again. So we've seen this before. And we're going to use what's called the Neyman-Pearson lemma. And so the Neyman-Pearson lemma said, suppose that y1 through yn are IID from some probability distribution with parameter theta. Suppose we want to test the simple null hypothesis, theta equal to theta naught, versus the simple alternative hypothesis, theta equal to theta a. So notice in this case, we're going to look at a specific place in the alternative for right now. So it's a little bit different than what you've seen before. So for a given alpha and a specified sample size, the test maximizes the power at theta, has the rejection region determined by the following. So we're going to look at a ratio of likelihoods, and we've looked at ratio of likelihoods before. And the value k is chosen so that the test has a desired value for alpha. Such a test is most powerful alpha level test for HO versus HA. So the proof here is pretty complicated, so we're not going to go over it. And then we just want to note here that if theta is equal to theta a, then L of theta a should be large and L of theta naught should be small. And if theta is equal to theta naught, then L of theta naught should be large and L of theta a should be small. All right, so let's look at an example. Suppose that y represents a single observation from the probability density function given by the following. We're going to find the most powerful test with significance level alpha equal to 0.05, and we're going to test under the null theta equal to 2, and under the alternative, we're going to test theta equal to 1. So let's look at how to do this. All right, so first of all, let's write out our likelihood. Now notice here, we just have a single y, a single observation. So our likelihood function in this case is just going to be equal to f of y given theta, which is equal to theta y, and then we got theta minus 1 in the exponent. All right, so let's look at the ratio. So in the numerator, I'm going to have the likelihood at theta naught, and in the denominator, I'm going to have the likelihood at theta a. So we're just going to substitute in those values. Right? And now notice under the null, theta is equal to 2, and under the alternative, theta is equal to 1. So let's plug in those values. Okay. So what this tells us is our rejection region is going to be 2y less than k. So we could stop here, but what we want to do is we want to find k so that alpha is equal to 0.05. Okay. So what we're going to do is we're going to rearrange this just a little bit, and we want to get y by itself on the left-hand side. So notice we could rewrite this as follows. Now, we really don't care what's on the right-hand side of this inequality, since it's going to be determined by the value of alpha. So what we can do is, instead of writing that as k is equal to 2, we're just going to call it c, because it's some constant, and that constant is going to be determined by alpha. So in general, when you work these problems, what happens is you might have to do quite a few different observations to get y by itself, but whatever you do over here on the right, you just keep track of it as c because it's a constant. We don't really worry about the original k. So now what we're going to look at to find this value of c, which is going to be based on alpha, is we're going to do the following. So notice that if we have f of y given that theta is equal to 2, remember that's what we had under the null. Notice this is going to be equal to 2y when y is restricted between 0 and 1 and 0 otherwise. And this is just coming from looking up here and plugging into the value under the null. So, remembering that alpha occurs when the null hypothesis is true, what we can do is we know that alpha is going to be equal to the area from 0 to c 2y dy. So integrating that. We find that c squared needs to be equal to 0.05. So therefore, c is going to be equal to the square root of 0.05. So anytime that we get our sample y less than the square root of 0.05, then we know that we need to reject. So therefore, the rejection region for the most powerful test where under the null we assume that theta is equal to 2 versus under the alternative theta is equal to 1 is y less than the square root of 0.05. All right. So let's actually calculate that power. So remember that power is equal to 1 minus beta, which is equal to 1 minus the probability that we accept the null given that the alternative is true Well, notice that's going to be equal to 1 minus the probability that y, and again, remember the reason I've got y here is for our example, we're looking at a single observation, greater than the square root of 0.05. Oops. Let me rewrite that line. Given that theta is equal to 1. So where are these coming from? So notice if we reject when y is less than the square root of 0.05, that means we would accept when y is greater than the square root of 0.05, and then under the alternative, theta was equal to 1. So to find that probability, we need integration. The 1 dy, that is coming from if again we went up here and we substitute in theta equal to 1. So notice our power here is equal to 0.2236, and that's a pretty small value. All right, so there is another example on the next page. Notice that this one is almost just like the last one. The only difference is now under the alternative, we're going to set theta equal to 3 is going to be the only difference. So I'd like you to try this one on your own. This will be your quiz question for this section. For this one, I'm going to grade it on completion. So all you have to do is try it, submit it to Blackboard, and then once you get it submitted, the solution will automatically appear underneath. And then this concludes the first part of the video, and the second part will be right below it.